Hi there, welcome you to the lecture series on control systems engineering. Today, we are in Industry 4.0 era. The industrialization started during the 18th century with the invention of steam engine, which you can call it as Industry 1.0 era. Earlier to that, the whole society was agrarian and artifacts were created manually. The Industrial Revolution got further boosted during the 19th century with the discovery of oil and the invention of electricity. Factories started creating products, goods using machines that we called it as Industrial Era 2.0. During the 20th century, automation was introduced in industry for manufacturing of products and goods, which we called it as Industry 3.0 era. Automation is the automatic operation or control of a process, device, or system. Automation is used to improve productivity and obtain high quality products. Now we are talking about smart industries, where not only automatic machines, even autonomous machines are used to manufacture and deliver goods, products, and even parts. The course Automatic Control Systems Engineering deals with the design, development, and operation of automatic machines or systems. Control system engineering is based on the foundation of feedback theory and linear system analysis. It integrates the concepts of network theory and communication theory. Therefore, control engineering is not limited to any engineering discipline, but is equally applicable to aeronautical, chemical, mechanical, environmental, civil, and electrical engineering. Now, let me start dealing with control systems engineering. The first session, I have titled it as Introduction to Control Systems. At the end of this session or class, students will be able to define a control system, identify control system components, illustrate simple control systems, represent a control system pictorially and block diagram form, and identify various signals in control systems. So to get an idea about what exactly a control system is, so let me play a video from YouTube.
Driving in heavy traffic is hard work. The driver needs to concentrate at all times, respond quickly to new situations, and react by braking or accelerating. With adaptive cruise control from Bosch, ACC for short, driving is far more relaxed. ACC can take the pressure off the driver during the journey by adapting the speed of the vehicle to the flow of traffic. The driver is thus able to better concentrate on the traffic situation and is supported in maintaining the safety distance to the preceding vehicle. ACC is easy to operate. The driver selects the desired speed and sets the distance to be maintained from the vehicle ahead. This distance can be set at several levels, adapting to the driving situation and individual driving style. ACC is now active. A long-range radar sensor monitors the driving situation ahead of the vehicle. The sensor transmits radar waves that are reflected by objects in front of the vehicle. Based on this data, ACC can detect preceding vehicles and can calculate the distance, direction, and relative speed of the vehicle ahead. When the road ahead is clear, ACC maintains the set desired speed. When the system detects that it is approaching a vehicle, it interacts with the engine control or the braking system in conjunction with the Electronic Stability Program ESP, and ensures that the set safety distance is maintained. Once the road ahead is clear, ACC automatically accelerates the vehicle to the desired preset speed. ACC supports harmonious traffic flow on the roads. Even when ACC is switched on, it remains the driver's responsibility to monitor the speed and distance from the vehicle ahead at all times. The driver can override or switch off the function at any time. The standard ACC can be activated from speeds of around 30 km per hour upwards and can support the driver, particularly on cross-country journeys or on freeways, up to speeds of around 200 km per hour. The ACC stop-and-go version is also active at speeds under 30 km per hour, right down to vehicle standstill. The system can maintain the set distance to the preceding vehicle even at low speeds and can brake down to complete vehicle standstill. When the vehicle ahead moves forward within a few seconds, the ACC vehicle follows automatically. When waiting times are longer, the driver needs only to reactivate the system, for example by briefly stepping on the gas pedal to return to ACC mode. In this way, ACC Stop and Go can support the driver even in heavy traffic and traffic jams. Both ACC versions can be realized by using just one long-range radar sensor. The tried and tested ACC functions can be further optimized via intelligent networking with surround sensors already installed in the vehicle, or by integrating additional video or radar sensor technology. This enables the ACC speed range to be extended from 200 to 250 km per hour and offers increased dynamics when driving off from a standstill. The ACC Sensor Control Unit is also a key component for implementing functions that enable a timely reaction to critical driving situations. More comfortable driving with adaptive cruise control from Bosch.
Bosch, invented for life.
Yes. That was a video on adaptive cruise control. Let us watch one more video, then I'll explain the concepts.
You're invited to a party and don't want to miss a minute of it. You want to get there as fast as possible, but without exceeding the speed limit, which is 50 miles per hour. In order to get to the party as soon as possible, you'll need to maintain your speed at 50 miles per hour. You may not have noticed it before, but actually you drive your car in closed loop. Let's first identify the components of this closed loop system, and then we'll learn the basic terminology. When you step on the gas pedal, your car's speed starts to change. You know that you want to be going 50 miles per hour. Let's show your desired speed on the plot with green. Notice that it remains constant over time. Next, you look at the speedometer to see at what speed you are. Let's show the monitored speed on this plot. Then you compare it to what you want. This is done by finding the difference between the desired and monitored speed, and it is called the error. Based on the error, you make a decision. In this case, the error is not zero, therefore you decide to apply more gas to get to your desired speed. And this in turn influences the speed of the car. The smaller the error gets, the less gas you apply. And once you get to the desired speed, you keep your foot still on the gas pedal to maintain your speed. Oh, I see. You already started dreaming. I'm sorry to interrupt, but let's go back to reality. Now that we identified the components, let's talk about how they are referred in control theory. In a feedback control system, the goal is to control the output to a desired value, and that value is referred as desired output. Other common terms are reference and set point. The object whose output you try to control is called the plant. The output of the plant is measured by the component called the sensor, and the measured output is then compared to the desired output. The difference between the desired and measured output is the error. Based on the computed error, the controller decides on the control action, and it commands an input which is then sent to the actuator. The actuator is how the controller influences the plant. In some situations, you'll see that the actuator, sensor, and plant dynamics are merged into one and referred to as the plant. This may sound pessimistic, but life is far from perfect. Sometimes things may go wrong. For our example here, it is the road grade. Imagine you're going uphill. Your speed will start to drop due to the hill, and you will need to press down further on the gas pedal to maintain your speed. Unexpected environmental changes causing the system output to behave in an undesired way, such as the road grade in this example, is called disturbance. Similarly, a sticky gas pedal, icy roads, or windy weather act as disturbance on the car. Another thing that may go wrong is related to measurement. While you're monitoring the speed, what if your vision is a little blurry because you forgot your glasses at home? The speed you're monitoring becomes noisy and fluctuates between values. This is referred as noise, which is an unwanted signal affecting your measured output value. Driving manually makes you tired. Cruise control can make your life easier. Let's see how the system can be converted to an automatic control system. Now, instead of monitoring the speed manually, you can have a device that provides an electronic measurement of the speed. Your brain was acting as a controller. Now, the engine control unit becomes the controller that computes a control action based on the error. The actuator now becomes a mechanical device that does what your foot used to do. In this case, the actuator is a motor that moves the gas pedal up and down based on the voltage computed by the controller. Now that you have the cruise controller fully engaged, enjoy your ride to the party.
Yes, that explains you the concept of control systems engineering. Now, you see here, I have shown a computer numerically controlled machine. We call it as in simple words, a CNC machine. This operates automatically. Suppose we want to produce a part, the drawing of which will be available to you. Say something like this with the dimensions, it will be available. Let us say we want to machine this part on a CNC machine. So what we do is we write a CNC program. What is CNC program? Basically a set of instructions. How exactly? The tool has to move in the X direction, Y direction, even the Z direction. So what tool it has to use? What speed it should machine? So all this information we write in a form of a program, a set of instruction. Once we feed that program, as per the program, the machine works and machines the part automatically. So CNC machine is a good example for an automatic system. Similarly, I have shown a robot, an industrial robot. Let us say its job is to pick this part from a tray and load it onto the machine. And as soon as the machining is completed, again it has to pick this machined part and put it into another bin. If that is the idea, again I write set of instructions, the program, and I feed this program. As per the program, the robot works automatically. So this is another good example for an automatic machine. Another very interesting example is that you face day to day, a traffic flow control. So how there are, you know that there are three lamps: green lamp, which allows the traffic to flow; yellow, okay, tells the traffic to be ready; and red, traffic has to be stopped. So now, if you have traffic, a large traffic over here, and this traffic has to move from this side to that side, let us say, then the green signal, like once the green lamp starts glowing, the traffic will start moving. How long this green lamp should glow? It depends upon what is the volume of traffic. If the traffic is less, the glow timing should be reduced. If the traffic is more, the glow timing should be increased. So that way, it is also operates in an automatic fashion. So you can call it as an automatic control system. Suppose we are talking about autopilot system when you are flying an aircraft. Correct? It has to fly from point 1 to point 2, right? A to B. It has to fly. First, it has to take off. Then it has to cruise. It has to take turns. All these kind of things happen. During this time, we have to operate various control surfaces for aircraft to take off, aircraft to cruise, aircraft have to take turn. Correct. Again, it has to land. So depending on that, we have to vary its roll angle, pitch angle, yaw angle, and all these kind of a thing. So using an autopilot, it is possible to do this. We call it as the flight control. It's also done automatically. These are all some of the examples of automatic machines. I think automatic control system engineering is all concerned with how to design and operate such systems reliably. So let me now give you a clear idea about with a simple illustration of illustration. So let me call this system as a water heating system. Water heating system. Now there is a word here, system. Let us understand the meaning of the term system first. For that, I'll explain this. Let us say I have a boiler. Here the idea is to heat this water. Okay, heat this water. The first question is, we have to heat this water to what temperature? Let us say we want to heat this water to a temperature of 80 degrees Celsius. Why 80 degrees Celsius? This is something a desired value. This is the temperature at which I want water for me for a process. This whatever 80 I am talking about, this value is the desired value. So I call it as a desired temperature. Here I have written desired temperature or set temperature. Where is it set? You see here we have an observer. He is interested in heating this water to a temperature of 80 degrees Celsius, is observer, and this value is set in his brine. So here you can see brine. The value is set in his brine. Next thing is, he will, to heat this water, various heating sources can be used. For explanation purpose, I'm using steam for heating this water. So first, he will allow the steam to flow through this. It's a coil through which the steam will be flowing. As the steam flows from the steam, the heat will be transferred from the steam to the water. So water absorbs this heat and its temperature starts increasing. At a given instant, he will look at the thermometer, which is recording the temperature over here. Let us say this at a given instant, the thermometer must have recorded a temperature of, let us say, 40 degrees Celsius or 50 degrees Celsius. Okay, whatever temperature that is recorded here, this is what you call it as an actual temperature. This actual temperature is recorded by thermometer. Here use the word thermometer, not temperature, thermometer. Okay, so the temperature is recorded on the thermometer. When the observer looks at the thermometer, that is his eyes will read the value, and that value is 50 degrees Celsius. Correct? He reads this information. It will go here. In his brain, the set value is 80 degrees Celsius, 80, and the brain generates an error. The error is the difference. This is 50 degrees Celsius, here 80 degrees Celsius. So error value is something like 30 degrees Celsius. The brain generates error. Not only that, next it should initiate action. So brain sends a signal to his hand. Okay. This hand is like an actuator. Like this hand, what it does is it tries adjust the valve. It opens the valve so that more steam can flow. Adjust the valve, more steam can flow. So more heat transfer can happen. So the temperature changes. Let us say it will reach to now 70 degrees Celsius. Like this, dynamically keeps adjusting till he achieves 80 degrees Celsius. So now he wanted a temperature of 80 degrees Celsius, and actual temperature is also 80 degrees Celsius. So he has achieved what he wants. But don't be under the impression moment he has achieved this temperature, he will shut off this valve and go. No. Okay, you are continuously drying. Maybe you are using this water. Its temperature might change. That time immediately he will read, he will generate the error, he will initiate the corrective action. So it is simply dynamic. Continuously it will be working in this fashion. Continuous. Okay. So such a system, I can call it as like no this one I can call it as system. So if what is system then? System is basically assemblage of components arranged in a particular fashion for accomplishing a desired job. So system is basically assemblage of components arranged in a particular fashion for accomplishing the desired job. What is the accomplishing of desired job here? Heating water to a temperature and maintaining that temperature continuously. That's the job. Okay, so the diagram what I have written, I call this diagram a schematic diagram or a flow diagram or functional diagram to visualize it. How exactly the system has to work and all that. The working procedure we can understand by drawing a block diagram. This I can call it as a block diagram. Okay, this is a basic simple illustration of a water heating system. So the definition is then what is a system? It is an assemblage of components, hardware and software. Okay, components arranged in a particular fashion for accomplishing a desired job. You can also say a system is one which establishes a relationship between output and input. Output and input. In this case, what is output? The desired temperature was the output. Right? Whatever temperature that you read, that is the output. And whatever the desired value or the set value is the input. So you can say a system establishes a cause and effect relationship. Right? That's how we can define a system. Sorry. Okay. Here you have seen there is a desired temperature. This is what I call it as input. Actual temperature is what I call it as output. All these things together you can call it as a system. So the system establishes a relationship between cause and effect. Now once again let us see. Here brain is what is like where the desired value is set. And again through the eyes the information of actual temperature flows in. It generates the error and initiates action. You can call it as controller. So this system has a controller. The system has a controller. But who is the controller here? The brain, the human being is the controller. So it's a human control system. Human control system. So again here, hand here is the one which adjusts the valve. You can call this as actuator. Correct. Again, hand is the actuator. This is an integral part, right? So it's a human control system. If I can replace brain by a controller, hand maybe some other like a electrical or mechanical device which can act as an actuator, then I can call it as a control system, or if it can operate on its own, you can call it as an automatic control system. Okay, now let me give another interesting example. A speed control system. Here, let us say you have an engine. Okay, what you call it as? Okay, and this engine, assume that it is driving an electric generator, a generator. Okay, and assume that this generator is supplying power to a locality, power. So I call this as now load. And this power has to be supplied, let us say at a frequency of 50 hertz. Okay. So to run at 50 hertz, this engine has to run at a particular speed. Let us say that speed is something like 1500 RPM. If this engine runs at 1500 RPM, then the generator will also be running at 1500 RPM and it will be producing power, let us say 50 hertz. So to get this speed, I adjust the fuel valve, say by adjusting the governor's flyball positions. This is what you call it as the governor. You can see here at this position, the governor here, this linkage is at this position, and so the valve, all these linkages are particular defined position so that the fuel is flowing and the engine is running at that speed. That speed, this setting, this position is, let us say, 4500 RPM. This is what I call it as set speed or desired speed. Okay, now the engine is running at that speed and it is just supplying power at 50 hertz, let us say. Okay, right. Now, due to some reason, let us say the load increases, means some more people will switch on the lamps or some motors or whatever it is, the load increases. Okay, so once this load increases, what happens? So the engine speed, a load on the engine increases, engine speed decreases. Let us say that speed is something like 1300 RPM. So here you can see here, once the engine speed decreases and has used a gear train system to drive this governor. So what is going to happen? So the centrifugal force decreases as this shaft speed decreases. The centrifugal force decreases, so that what is going to happen is the fly balls will move towards the shaft like this because less centrifugal force. When these fly balls move towards this, what's going to happen? This linkage will push this sleeve down. When this sleeve pushes goes down, then you can see this linkage will incline position. It will take a position like this. So when it can take the position like this linkage will move up. So when this linkage moves up, here I have another, valve control system, a piston cylinder arrangement. You can call it as a spool valve. Then what is going to happen? Oil from oil pump will enter like this. It will exert a force on this so that this will move up. The valve will open. So more fuel enters and again engine speed increases. So fly balls were in this position. The desired position of the fly ball is this. Now again the fly balls will start moving outwards. So to maintain that speed. Okay, this is how this system works. So now the question is, here the desired speed is 1500 RPM, set RPM. How do I set? By this fly ball positions on the governor. Okay, governor is basically a controller now. Actual engine speed is transferred to the governor through gears, and because of that the fly ball position changes. The set position of the fly balls and new position of the fly ball will give you the difference. That is what you call it as error. Based on that, the sleeve of the governor will operate these mechanical linkages, and these mechanical linkages in turn will operate this valve and vary the fuel flow and control the engine speed. This is what you can call it as a speed control system. So here, this you call it as set value or the desired value. This you call it as the actual value. Okay, the variation in load or whatever it is, you can call it as a disturbance. If there is no disturbance, continuously it will be working. The moment there is a disturbance, there will be change in these parameters and immediately it will initiate a corrective action. That is where, so now the governor becomes the controller. These mechanical linkages, they will become actuators, and engine becomes the plant, and gears will act as feedback devices. So control system, this is what I have said. Governor, you can call it as controller. Mechanical linkages, you can call it as actuators. The valve and engine is an integral device. Let me call it as a plant. Gears, we call it as feedback device. The set RPM, we call it as a reference signal. And actual RPM, we call it as a controlled variable. And the speed of the governor shaft, that is what we call as a feedback signal. The difference in the fly ball position, that will give you the error. That in turn will actuate the sleeve position. The sleeve in turn will actuate the mechanical linkages. That's how it works. This you can call it as a control system. And these are the terminologies that we use: controller, actuator, the plant, the feedback. So you can call it as a feedback system. Now let us take some complex example. So nowadays, most of the cars are fitted with electronic stability program. You call it as ESP, or you can call it as a yaw control system, right? So I'll just explain how exactly it acts as a control. How I'll illustrate this to explain how it is a control system. Imagine it's an highway. It's an highway. Imagine it's an highway. You are driving your vehicle in this lane. Let us say you are driving your vehicle with high speed. Let us say 180 kilometers per hour. That's the speed with which you are driving. While you are driving, an unseen, like you are unexpectedly a car enters into this lane. Now you want to avoid this, to avoid the accident. Then what do? You immediately take a turn like this. This is now a corner. So automatically a centrifugal force comes into picture, which is given by W by G, V squared by R, where W is the weight of your vehicle, G is the acceleration due to gravity, V is the speed of your vehicle, R is the radius of the circle. Okay, now you can very clearly see that you are taking a small turn, that is R is very small and V is very high, and the centrifugal force is very, very high. So it may throw away your vehicle. Okay. So the whole vehicle may start turning like this. You see here, it is like this. It is start turning like this. So you may lose completely the control. So your vehicle becomes, you can say, unstable. Now the question is, the centrifugal force disturbed it. That's fine. Now we have to see what needs to be done. How do we put this vehicle on lane? So now I have to create a counterclockwise moment. Counterclockwise moment. Suppose if you see, these are the four wheels, and if I can apply a brake at this wheel, this is a brake force, and this is the center of gravity of the vehicle here. Force into this radius will give you moment, and this brake force may create a counterclockwise moment. And it should be just equal and opposite to that, so that it can keep the vehicle on track. That's what exactly we do this. This is what you call it as an yaw control or oversteer control of a car. So as I mentioned, here the car is the plant. Car is the plant. You are applying a brake force. That is what you can call it as actuator. Now the thing is, we have to have lots of sensors. So lateral acceleration, when vehicle is moving, V squared by R, you can call it as a lateral acceleration. It has to measure that lateral acceleration. To calculate this lateral acceleration, of course, we know vehicle speed and all that. And intention of the driver, in which direction the driver wants to know. So steering angle is necessary. All these are measured. So now here you see the controller now will decide what is the intended direction and the direction at which the vehicle is moving, yawing. So how much yaw control has to be initiated? So for that, how much force, counterclockwise moment has to be created? This will decide and accordingly decide what should be the brake force and so much of brake force and where exactly the brake force has to be applied, and it will apply that and it will control this system. This happens automatically. So now it is not so easy, simple. So there are many sensors here, and we have to write proper, controller program and see and write. So we need to bring in the required physics and the required equations in here and to control such kind of a system. Okay, now just for example, just to make you something like interesting to visualize this, let me play this video from Bosch.
I've been taking this route for over 8 years now. 5 days a week, 200 days a year, to work and back.
He went first and then he said, do you want me to show you?
How do you do it?
Nowhere practically every tree is, every bend.
Look, a light's come on. What is it?
It's the bit here through the woods I like best.
Oh, where's that fuel canister gone?
Shouldn't we put up the warning triangle first? Do you think that's far enough?
No, beyond the bend. It's much too dangerous. Hurry!
A bit later setting up that triangle and... Webers? You still haven't got the list? Uh-huh, I see. In that case, I'll have to stop by before the meeting. Where on earth can the list have got to? Heaven knows what else will happen today. I'll be there in 5 minutes. I can sort it out from there. That sheeting isn't going to stay on much longer. In everyday driving, it's normal for transverse forces to arise. But when you drive a bit too fast or turn the steering wheel, these forces can negatively affect road holding. But the Electronic Stability Program ESP nips that in the bud by controlling the brakes, if necessary the engine, and if need be the transmission as well. ESP comprises the following components: a speed sensor on each wheel. The rotation rate sensor measures the car's rotation around its vertical axis. The steering angle sensor registers the driver's steering intention. From the sensor signals, the control unit computes when and how it has to intervene. The hydraulic unit builds up and reduces the braking pressure in the brakes. What happens during the first steering maneuver? The driver has to swerve quickly to the left. The steering angle sensor transmits this to the ESP control unit. But the rotation rate sensor signals that the car is understeering. That is, it's drifting straight ahead towards the obstacle. In split seconds, ESP brakes the left rear wheel, very briefly and sharply. This produces the desired counteracting force so that the car responds as the driver intended. What happens when you react? When you pull the wheel over to keep the car in the left lane after avoiding the obstacle, the car tends to oversteer, and the rear end tends to brake away to the left. The torque to the right is higher than the driver wants. In this case, ESP brakes the left front wheel. The torque is reduced. Instead of going into a skid, the car stays on course, thanks to ESP. Probably hasn't even noticed.
So you've seen a beautiful example now. So another very interesting example like this, I can also talk about an anti-lock braking system, ABS system. So you must have experienced while driving your car. So when you are driving very fast, if an obstacle comes, all of a sudden you try to apply, a panic braking. So you ram on this. So that your idea is that let more brake force be applied on this and let the vehicle stop. So what really happens is when you apply brake like this, I call that braking as panic braking. So when you do that, this wheel will stop spinning, means rotating, but does not mean the vehicle will stop. Then will simply the vehicle skids. So that is what we call it as a wheel locking condition. So once the wheel gets locked, though vehicle is moving, but you cannot steer the vehicle. So it makes your vehicle unstable and unsafe. So whole idea is that we want to avoid the locking of the wheels, but we want to slow down the vehicle. And so that you will have the freedom of steering the vehicle away from the obstacle. So that is what we call it as an anti-lock braking system. So here really how exactly it works is possible. I can explain this, but anyway, just let me tell you here. Our intention is to slow down the vehicle and you should be able to stop the vehicle and all that. So actual vehicle speed is measured. There are two things here. We'll talk something like slip over here. We talk about slip. Slip is defined as V minus omega R divided by V. Here V is the vehicle speed and omega is the angular velocity of the wheel. R is the radius of the wheel. So when we draw vehicle speed versus, or we can say wheel speed versus percentage slip. So you can see something like when the slip is 100%, when you mean by slip is 100%, omega value is 0. but vehicle velocity will be there. So that is what we call it as a locking condition. So we do not want the wheels to get locked. So now let us say this is the speed with which the actual vehicle speed, let us say. Also, you can measure what is the wheel speed, omega, vehicle speed as well as say wheel speed, both you can mark over here. Okay, actual speed, vehicle speed sensor will measure the wheel speed, sensor will measure the wheel speed, vehicle speed sensor will measure the vehicle speed. This information will go over here. Okay, the value of V is substituted, omega is substituted, slip is determined. Now we want to have a slip between something like 18% to let us say 22%. Within that only we should manage the slip value. Below 18 also not good. About 22, again it will start moving towards locking. That means when we apply brake at this point, let us say wheel speed will start decreasing, so also the vehicle speed will start decreasing. Wheel speed sensor will measure omega, vehicle speed sensor will measure the omega, it will measure the slip. If his slip is more than 22%, what it does is ECU sends a signal to release the brake. Release the brake means again the speed will increase. Again it will measure the slip. It is below 18% means again it will apply the brake. Again slip will start increasing, again release the brake. Like this, apply, release, like this it will stop the vehicle. Finally it will stop the vehicle, but it will not lock the wheels. This is what we call it as ABS system. Correct? And you can play this YouTube video, you can understand how exactly an ABS system works. So this is also a feedback control system. So I have given lots of illustration idea about what exactly control system is. So let us understand some terminology for the future. Plant. The physical system whose dynamic behavior needs to be controlled is plant. ABS, car is the plant. ASP, car is the plant. Water heating system, yes. Furnace is the plant. Speed control system, engine is the plant. Like this, plant. Physical system whose dynamic behavior needs to be controlled. Dynamic behavior, that's a very important thing. So control system deals about dynamic systems. Controller is this one. It controls the plant behavior. What exactly it does? It measures the feedback, compares the feedback signal with the reference signal, generates the error signal, and initiates a corrective action in a particular way. That is what controller is. So a system with controller, you can say like, a control system. Controller normally what it does is, it is, operates the, when it initiates the corrective action, it operates the actuator. So actuator job is, you have seen, either it is opening the throttle or closing the throttle, whatever it is, it's basically, it can be a mechanical device, it can be an electrical device, it can be hydropneumatic, whatever it is, right? So we use the actuator plant. Okay, then there'll be a measuring device, output measuring device, that's what we call it as the feedback device. So together you can call it as an automatic system. So the system is assemblage of components arranged in a particular fashion to accomplish the desired job. It establishes a relationship between the output and the input. Automatic control system is one. Here, a comparator compares measured output, that is feedback signal, with the input, that is reference signal, and generates an error signal, and controller initiates the action to reduce or eliminate this error. The system works without human intervention. That's why you can call it as an automatic system. Okay. I think error signal actuates the controller in a particular way so that the output signal from the controller will have a definite relationship with the error signal. Okay, these are the terminologies that we use with the control system. So this gives you an idea about what exactly the control system is, and the course deals about how to design, how to improve the system behavior, how to design and develop controllers, feedback devices, and actuators so that you get the desired output. Summary: an automatic control system measures the output variable, compares it with set or desired value, generates an error signal. The error signal initiates appropriate corrective action through an actuator so that the planned output achieves the desired value. There are something like we use the word CISO. They are single input and single output control systems. Many of them I explained like single input and single output. MIMO, there are multiple input and multiple output control systems, and they are quite common nowadays. So in the present course, we'll focus mostly on CISO systems. Okay guys, and this is what the introduction about control systems. I'll I'll continue further in the next video. Till then, thank you very much.